In this video, we are going to calculate the probability of one event and a second event occurring. So whenever we have one event and a second event, we are going to multiply. So we have two definitions. The first one, we have independent events. So if the occurrence of either event has no effect on the probability of the other. And then dependent events, if the occurrence of one event has an effect on the probability of the other. So an example of an event that is dependent is if you're drawing cards from a deck. And if you take a card out and you don't replace it, then that second event depends on whatever your first event is. So whatever the first card is that you've drawn. Our notations and formulas, if they are independent events, then you're just going to take the first probability and multiply it by the second. If they are dependent events, then you're going to take the probability of the first event and multiply it by the probability of the second, given that the first event has occurred. So let's take a look at these. On our first exercise, we are going to use the spinner shown to solve the following. It is equally probable that the pointer will land on any one of the 6 regions. If the pointer lands on the borderline, spin again. If the pointer is spun twice, find the probability that it will land on yellow and then yellow. So we're going to ask ourselves if these are dependent or independent events. So does our second event depend on our first event? And the answer is no. So these are independent events. So let's look at our spinner. We have 6 total spaces that we can land on, and there's only one of those that are yellow. So we have 1 out of 6 probability for each of these events. And whenever we multiply these together, we get 1 out of 36. Alrighty, on B, we want a color other than red each time. So we want the probability of not red and then not red again. So let's look at our spinner. We have 1, 2, 3 that are red. So that means that we have 3 that are not red. So we have 3 out of 6 that are not red. So 3 out of 6 times 3 out of 6. You can either multiply or you can go ahead and reduce down. We have 1/2 times 1/2 gives us 1/4. Okay, number 2, you draw 1 card from a 52 card deck. The card is then replaced in the deck is shuffled, and you draw again. Find the probability of drawing. So since we replaced the card, we are working with independent events. So we want, on A, we have a jack the first time and a club the second time. So probability of a jack and a club. We have 4 jacks out of 52. And then how many clubs do we have? Clubs are our suit. So all of these are clubs. So we have 13 out of 52. Alright, you can multiply these two fractions, or we can go ahead and reduce. So I'm going to reduce. We have 1 out of 13 times 1 out of 4 gives us 1 over 52. Alrighty, what is the probability of drawing a king each time? Okay, how many kings do we have? We have 4 kings from our deck of cards. So we have 4 out of 52 times 4 out of 52. That reduces down to 1 over 13 times 1 over 13. And that gives us 1 over 169. Okay, and then on the last one on C, we want a red card each time. So let's look at our deck of cards. Half of them are red and half are black. So half are red gives us 1/4. And then our last one, consider a political discussion group consisting of 5 Democrats, 6 Republicans, and 4 independents. Suppose that 2 group members are randomly selected to attend a political convention. Find the probability of selecting 2 Democrats. So these events are dependent events. The second event depends on our first event. So that means we're going to find the probability of a Democrat and then a Democrat. So we take the probability of the Democrat the first time, multiply it to the probability of a Democrat given the first was a Democrat. So our Democrats, we have 5 Democrats. What is the total number of people that we are choosing from? We have 5 Democrats, 6 Republicans, 4 independents. So we have 15 people total that we are choosing from. What is the probability of choosing that second Democrat? Well, if we have already taken 1 out of there, then we only have 4 left. And then that also means that if we had 15 people to begin with and we took 1, we only have 14 left. Okay, so we get 20 over 210, and this reduces to 2 over 21. All right, on B, we want an independent and then a Republican. All right, the probability of an independent. We have 4 independents out of the 15 people. And then our Republicans, we have 6 Republicans, but we don't have 15 people anymore. We only have 14. So we get 24 over 210, and that reduces to 4 over 35. And then our last exercise, we want no Democrats. So probability of not drawing a Democrat. We have 6 Republicans and 4 independents. So we have 10 people we can choose from out of 15. If we take 1 person out of those 10, we only have 9 left. And if we take 1 person from the 15, we have 14 left. So we get 90 over 210, and that reduces down to 3/7. We are going to compute conditional probabilities. So conditional probabilities are the probability of the event B assuming that A has already occurred. So whenever we have 2 events occurring, we are going to take into account the first event that has occurred. So if we have the probability of B given that A has occurred, we are going to take the number of outcomes common to B and A divided by the number of outcomes in A. So on our exercise, we have the numbered discs. They are placed in a box and 1 disc is selected at random. Okay, so we are going to find the probability of an odd number given that the disc is blue. So the way that this works, we are going to take the number of discs that are odd and blue and divide by the number of discs that are blue. So the number of discs that are odd and blue, we have 1, 2, 3, okay? And then the number of discs that are blue, we have 1, 2, 3, 4, 5. So we have 3 out of 5 for this one. On B, we want a green disc given that an even number is selected. So we're going to have the number of discs that are green and even on top divided by the number of discs that are even. So the discs that are green and even, we have one right here, one right here, so we have 2. And then the total number of discs that are even, we have 1, 2, 3, 4. So 2 out of 4 reduces to 1/2. Alrighty, this last exercise, we have car accidents in Florida. And we have it broken up by the people who lived and the people who died, and then the people who wore seatbelts and did not wear seatbelts. So using the table above, find the probability of surviving a car accident given that the driver wore a seatbelt. So the number of people who survived and wore a seatbelt is 412, 368. And then the number of people who wore a seatbelt is 412, 878. So they want these answers as decimals. So we get 0.9987, and we're going to round it to 3 decimal places, so 0.999. Alrighty, on B, we're going to find the probability of not surviving a car accident given that the driver did not wear a seatbelt. So on the top, we have the total number who died and did not wear a seatbelt. So died and no seatbelt, we have 1601. And then the total number of no seatbelts was 164,128, which is 0.0097. We're going to round 0.010, 3 decimal places. Alrighty, on C, find the probability of wearing a seatbelt given that a driver survived a car accident. So we have the number of people who wore a seatbelt and survived divided by the number of people who survived. So the number of people who wore a seatbelt and survived, 412, 368. And then the total number of people who survived, 574, 895. Okay, whenever we divide, we get 0.7172, and that rounds to 0.717. All right, the last one, find the probability of not wearing a seatbelt given that a driver did not survive. So we are going to have the number of people with no seatbelt, the number of people with no seatbelt and died, 1601, divided by the total number of people who died, 2111. So we have 1601 divided by 2111 gives us 0.7584. And we're going to round to 0.758.